Paper is pretty basic, so I didn't want to take anything away from Thea. Okay, so how many guys are Geo kids? I know you are. Okay, yeah.
Raise
so
your
for
hands
the rest
high,
of us,
I want to make...
yeah, be proud of that.
Yeah.
So, for the rest of us, I know I need a refresher, so I'm assuming the other bio kids do.
Yes, please.
So, I'm going to take you guys step by step through the geological time scale. We're going to start with the Precambrian and work our way down through the Cryogenian. So the Precambrian started at the creation of the Earth, which is around 4.6 billion years ago, and lasted around, it ended around 543 million years ago. So some important things that happened during this time period. The Earth cooled from its molten state and developed a solid crust. Oceans were created from the water vapor that was in the atmosphere, and it's thought that primordial seas gave rise to life. So volcanic vents act as catalysts for chemical reactions across the surface of water bubbles, and these were the very first basic cell membranes. And then other bubbles are thought to have formed self-replicating substances by attracting chemicals from around them. So over time, these two types of bubbles combined to produce energy using living cells. And these are the first microscopic bacteria, and they show up in the fossil record around 3.4 billion years ago. Okay. And the Precambrian is made up of 3 eons, and we're going to focus on the Proterozoic. It started 2.5 billion years ago and ended 541 million years ago. It was dominated by the formation of supercontinents. 2 notable ones are Columbia, which was created about 2.2 to 2.1 billion years ago, and Rodinia, which was created around 1 billion years ago. Another important event that occurred in this eon was the accumulation of oxygen in the atmosphere. It's really important. And the Proterozoic is made up of 3 eras, and we will be talking about the Neoproterozoic. It occurred 1,000 to 541 million years ago. During this time, Rodinia broke up into smaller land masses, and the first multi-celled organisms known as trilobites appeared. Okay. So the Neoproterozoic is made up of 3 periods. We're going to focus on the Cryogenia. So this was from 720 to 635 million years ago, and the Stritian and Moronian glaciations occurred during this time period. The Stritian glaciation lasted 715 to 680 million years, and the Moronian glaciation occurred 680 to 635 million years ago. Okay. So now I'm going to talk about some of the ideas that led up to the idea of Snowball Earth, because we all know an idea like Snowball Earth just doesn't happen overnight. So, it all started with Douglas Mawson. He was an Australian geologist as well as an Antarctic explorer. He studied the Neoproterozoic stratigraphy, which for us non-geo kids is the study of rock layers. And he did his study in South Australia. He identified glacial sediment and speculated about possibility of global glaciation. However, he didn't take into account continental drift, so he assumed that the glaciation occurred at current latitudes. Next is Brian W. Hartland. He published a paper in 1964. In this paper, he presented paleomagnetic data that showed that glacial sediment in Svalbard, which is a small island nation off the northern coast of Norway, and Greenland were deposited at tropical latitudes. Glacial sediments among rocks associated with tropical and temperate latitudes led him to argue for an ice age so extreme that it resulted in the deposition of marine glacial sediment in the tropics. Next, we're going to talk about the Russian climatologist Mikhail Budko. He developed an energy balanced climate model to look at the effect of ice cover on global climate. He found that if ice sheets advanced far enough out of the polar regions, a feedback loop ensued, where the increased albedo of the ice led to further cooling and more ice formation until the entire Earth was covered in ice. His model showed that an ice albedo stability could happen, but he concluded that it never had because his model didn't provide a way out of this. Aaron Faegre was an American physicist, used a similar energy balance model, and predicted 3 stable global climates, one being Snowball Earth. And he said that there could be a major jump from one climate to another. Joseph Kiersvich is the man who coined the term Snowball Earth in a paper published in 1992. There are 2 major contributions from this paper. First, the recognition that the presence of banded iron formations is consistent with the major glacial episode. And 2, the introduction of a mechanism in which we could escape an ice-covered Earth. He proposed that the accumulation of CO2 from volcanic outgassing could lead to an ultra-greenhouse effect that would melt the ice. Paul S. Hoffman applied Kiersvich's ideas to Neoproterozoic sedimentary rocks in Namibia, and he observed the occurrence of cap carbonates, which is layers of limestone or dolostone that overlay Neoproterozoic glacial deposits. And this added to the Snowball Earth hypothesis because it indicated that a rapid change in weathering during the extreme greenhouse Baldy glaciation. So it kind of just said, like, there was a cold time and then there was a lot of greenhouse gas due to the volcanoes that kind of like capped everything off and gave like a very defined layer that we could look at. And Francis McDonald, he's an earth scientist at Harvard. He's working with volcanic rocks in Canada that were found between glacial deposits. And he and his team used uranium-lead mass spectrometry to determine that both the volcanic and the glacial deposits were deposited about 716.5 million years ago. And he matched his findings to previous magnetic studies and found that these rocks had formed when Canada was near the equator. He proposed that Earth was more of a mud ball than a snowball. He said eruptions of volcanoes would cover ice and dust, and that this dust-covered ice would be the only dark spots on Earth to attract the sun's rays, and they may be more likely to melt, which would provide an area for primitive life forms to survive in. And that led to later diversification in the Cambrian explosion. So the Cambrian explosion started between 570 and 530 million years ago. It led to the appearance of most major animal phyla that we have today, and it only lasted about 30 million years. So some of you may be wondering, like, how did this change occur so fast? There are 2 ideas. First is the increase in oxygen that began around 700 million years ago, provided the means for movement and the evolution of more complex body forms. And the second is the extinction, like Snowball Earth would provide, of life before Cambrian that opened up adaptive space that new forms could exploit. These 2 ideas help to explain how simple-celled bacteria evolved into every animal in history, including
Thanks, nice work.
Good, solid, man. I'm gonna end up saying like a couple of things that you said. It's alright. It's because me. So that was Halee.
You're good.
Dang it.
Good.
Halee. That was Halee's very wonderful introduction, and now I'm going to talk about the actual paper. Models on Snowball Earth and Cambrian Explosion, a synopsis. And basically, it's a synopsis because these 2 guys, Mariana and Santosh, just took a whole bunch of other models and combined them into one paper and really like got just the basic meat out of all these other papers. So the idea of Snowball Earth, we just talked about it. Basically, it's just the idea that at one point in time, the entire Earth was covered in ice. And there's evidence that supports this, and those are things like the glacial debris, the paleolatitudes, which is just the idea that at one point in time, a specific latitude was at a different place because of continental shifts and changing in poles, which is why there was tropical deposits in Greenland. And then also the cap carbonates, which is the limestone on top of glacial debris, and chemostratigraphy, which is how we know that all of these deposits are as old as they are. which you could argue about, I suppose. The four main models that this paper covers are the greenhouse gas model, the true polar wander model, geomagnetism, and galactic cosmic rays. So I'm going to start with the greenhouse gas model. The greenhouse gas model basically says that there's only one main input of atmospheric CO2 and one main sink of atmospheric CO2. And the input comes from volcanic activity, and the sink comes from the CO2 going into the mantle through erosion, where it becomes bicarbonate and is no longer inorganic CO2. I mean, bicarbonate is still inorganic, but it's no longer CO2. So basically what happened was that there was a lot of continent movement, and the continents created a lot of erosion, and all of the CO2 got sucked out of the atmosphere, so there was no longer the greenhouse effect on the Earth, and all of the heat just escaped. So we ended up with a very cold Earth and ended up with Snowball Earth. However, during this time, the volcanoes are still really active because volcanoes don't care about ice. And the volcanoes put out a lot of CO2, and according to this model, the Snowball Earth disappeared because of volcanic activity putting CO2 in the atmosphere. So that's the first model. And then the second model is the true polar wander model, which says that at one point in time, all of the continents were up towards the poles, and then they all moved towards the equator, which really changed the dynamic of the way that light was reflected and absorbed on the Earth, and you end up with Snowball Earth. So in relation to the movement of the continents, you have all the continents sitting on the crust and the lithosphere, which is the movement of all of those things is controlled by the mantle, whereas the magnetic field of the actual Earth is controlled by the outer core. So true polar wander just basically says that things on the surface of the Earth shift without the poles ever actually shifting.
Can you say that again, please?
So true polar wander is basically that
I just don't get it, so you just repeat the same thing, it'd be fine.
The poles don't change, but the movement of the continents does, so it's like the orientation of the Earth on its axis changes.
And when you say poles, what I don't get is do you mean the pole on the surface of the Earth, or do you mean the pole as defined by the
magnetic
inner core?
pole. The magnetic pole.
Okay.
So you have the change of the you have the change of the Earth without changing the magnetic orientation, which ends up forming clouds, and then you have Snowball Earth. And then when the continents shift back, then Snowball Earth goes away. So that's the second model. And then the third model is geomagnetism, which is kind of a combination of true polar wander and cosmic rays, which is the fourth model. What you have is that normally the Earth has a dipole, and you have a north and a south pole, and the magnetic field exists the way that it does. And then you have something called equatorial downflow, which is basically the movement of the dynamic of the pole being controlled by the core to the pole is then controlled by the mantle. Like the electric field is no longer coming from the center of the Earth, it's sort of coming from the mantle. And when that happens, you end up with a loss of magnetic field, and you form ice sheets and more clouds, and Snowball Earth happens. And then when the magnetic field strengthens again, Snowball Earth goes away. They think, they're not 100% sure, but they think the main reason that the magnetic field strengthens or weakens is because of cosmic radiation, which is how true polar wander ties in with cosmic rays and you get geomagnetism. And then the fourth one is the cosmic rays in the galaxy, where this dotted line is the orbit of our solar system within the galaxy, and anytime it crosses one of these galactic arms, which are the thick blue lines, is when we get bombarded with a lot of cosmic rays and gamma rays, and it really creates this process where we have higher energy radiation hitting Earth, which brings in the space dust, and then that gets trapped in our atmosphere, and we have the heavy cloud formation which reflects all of the sunlight, and Snowball Earth happens. And then the supposed way that we come out of Snowball Earth in this model is that we move out of the path of the cosmic radiation. So those are the four models, and I mean, they each are just models, so it's hard to really understand if one could be more viable than the other. But it's, they all try to explain the idea behind Snowball Earth. And then after this happened, we have the Cambrian explosion, which, so there was the Snowball Earth event, and the entire Earth was covered in ice, and it shifts then to being thawed, and you have a lot of nutrients being dumped in the ocean, and atmospheric O2 rises, and then also you have this cosmic radiation which aids in mutation, and then you have the explosion of life. So it's an interesting transition from this ice ball that's pretty much void of life to the world we have today. Are there any immediate questions?